This is a continuation from the very first video on balancing chemical equations. If you have not seen that one, I would advise you to look at that video before proceeding with this one. But in that video, at the very end, you were promised a look at two so-called tricks of the trade to help balance chemical equations, and those tricks were fractionation and cross-multiply. So now let's look at an example that illustrates this idea of fractionation. What we will consider now is to balance the reaction of the oxidation of ethane, C2H6. It's very similar to one we did earlier, methane, only there is a noticeable difference that will require us to use the concept of fractionation. And with that, let's get to it. Last time, remember, the first thing that you're supposed to do is identify any pure elements, and we see oxygen as a pure element. And the next step is to identify any paired elements. And paired elements are elements that appear once and only once on each side of the equation. And so we first consider carbon. It appears once and only once on each side of the equation. And as well as hydrogen. Hydrogen appears once on the reactant side and once on the product. Oxygen, notice oxygen appears once on the reactant side and twice on the product side, so it is not paired. And with that, we agreed we would start with the paired element with the largest subscript. In this case, the hydrogen in ethane. And so with that, let's begin by locking that, as it were, down at 6 by putting a coefficient 1 here. If we have 6 on this side, then we must have 6 hydrogen on that side. 3 water molecules, each water molecule having 2 hydrogens, is a total of 6. Hydrogen is now balanced. Returning now to the reactant side. If there's 6 hydrogens, there must necessarily be 2 carbons. If there's 2 carbons on the reactant side, there must be 2 on the product side. I can only get 2 on the product side by putting a coefficient of 2 in front of the carbon dioxide. And with that, everything is balanced except for oxygen. And the coefficient in front of oxygen is the only one left with which I have to work. So let's set up our simple equation. I have 2 times 2, which is 4 oxygens from the carbon dioxides, and I have 3 times 1, so I have 3 oxygens for a total of 7 oxygens on the product side. So I need some number times 2, because whatever coefficient I use in front of the oxygen, I have to multiply that by 2. I'm going to write it this way. So what number times 2 will give me 7? Well, I know if I take a 7 and put a 2 in the denominator so I can cancel these out, I get 7 halves times 2 must necessarily equal 7. And there you have it. That is what we mean by fractionation. I have now used a fraction to balance this chemical equations. Oh, are my oxygens balanced? Yes. I have 7 halves times 2, which gives me 7. And on this side, I have 7. So this equation is indeed balanced. But there's a separate question here. Is it in the proper form? No, it is not in the proper form. It is balanced, but it is not in the proper form. By proper form, we have to have integers in front of each of these, and they have to have the smallest integers possible. So, to remedy this situation is very, very simple now. Maybe I'll use a different color, blue. What I need to do is to get rid of this 2 so that I, in essence, remove the only fraction that I have. So I'm going to do that by just using a basic mathematical trick of multiplying this fraction by 2. But the rule of math requires whatever I do to one thing in a mathematical equation, I must do to everything if that equality is to be maintained. So here we go. I'm going to multiply everything by 2. So this becomes 2. This 2 is canceled out by that 2. This 2 now goes to 4. 2 times 2 is 4. That is hard to see. Sorry about that. And this 2 times that 3 goes to 6. So now let me rewrite our final equation. And there you have the balanced chemical equation using fractionation. Now let's look at another example to see what cross multiply might look like. And for that, we're going to take antimony and react it with chlorine. So here, if we do the same thing, we will see that as far as identifying lone elements, this is lone, are pure, and that's a pure element. And so now let's identify the paired. Well, this appears once and only once, and this appears once and only once. So let's start with our paired element with the largest subscript. Now we might be tempted to put a 3 halves here. Why? Well, because if we need to use a fraction to get rid of this, we would have to use a fraction to get rid of that 2 and to add the 3 to make these the same. But oftentimes starting with a fraction can be kind of tricky, because if we then need to use the trick of fractionation a second time, we end up with fractions of fractions, which can be fairly difficult to work with and fairly tricky. So what we're going to do is use the second trick. We see that that's a small number, and that's a 3, and this is a 2. And so when one of these is odd and one of these is even, you can use the trick of cross multiply. We will multiply this one with the 2 by the 3, and this formula here with the 3 subscript by a 2. So that we have 3 times 2 is necessarily equal to 2 times 3. In other words, cross multiply. And now we know that this chlorine is balanced. If we have a 2 coefficient, that means antimony is locked in at 2, and so we merely put a 2 here. And now this equation is balanced. 2Sb, 2 antimony, plus 3 chlorine molecules is equal to 2 antimony trichloride. And that equation is now balanced using cross multiply. Let's do one more where we combine these so you can see the utility. This is a little bit harder problem, and so let's look at that. This is the oxidation of ammonia. So let's first begin by our usual. This element is pure, and let's identify lone elements. Nitrogen appears once and only once on each side of the equation. Hydrogen appears once and only once on each side of the equation. Oxygen appears twice on this side and once on that. And our general rule is we're going to begin with the paired element with the largest subscript. In this case, this 3. Rather than lock this down at 3, I'll look over and see that's a 2. That's odd, that's even, they're small numbers. So I'm going to choose to, rather than use some fractionation, in which case to get these to match out, I would have to put a 2/3 here. Yes, 3 to cross that out and a 2 to match that. Rather than go to fractionation, when I have a choice, I'm going to go to cross multiply when I have one small odd and one small even. Now you can see that the hydrogens are balanced. So the nitrogen now must be 2. If it must be 2 on this side, it must be 2 on this side. And now I have my old situation where I have some fraction times 2 is equal to 2 oxygens plus 3 oxygen. So I've got to have some fraction is equal to 5. And what do I need? I need a 5 to show up and a 2 to go away. Yes? So I'm going to put 5/2 there. So notice this equation becomes fairly easy, but realizing that first I use the trick of cross multiply, and now I'm using the trick of fractionation. And as we know, all we have to do now, I'll try a different color than the blue. All we have to do now is get rid of this 2 by multiplying everything by 2. 2 times 2 is 4. 2 times 5/2 is just 5. 2 times 2 is 4. And 2 times 3 is 6. And finally, to rewrite this last equation, what do we have here? A total of 4 ammonia plus 5 oxygen gives 4 nitrogen monoxide and 6 water molecules. And that should be completely balanced. And with that, I hope you can see a good review of the general process of identifying pure elements and paired elements, starting with the largest paired element, but always looking for, if you can, an opportunity to use the 2 tricks of the trade I just gave you. Cross multiply first, and then fractionation as well.